Lipid metabolism beta oxidation 2. This slide presentation will review the 4 steps of beta oxidation. As a reminder, this process occurs in the mitochondria, reducing a fatty acid chain by 2 carbons. The 2-carbon molecule cleaved is acetyl-CoA. The 4 general steps of beta oxidation can be classified as oxidation, hydration, oxidation, and cleavage, leaving the fatty acyl CoA 2 carbons shorter and an acetyl-CoA. The first step of beta oxidation is an oxidation reaction, also known as a dehydrogenation reaction. In this reaction, a hydrogen attached to the carbon 2 and carbon 3 molecules are removed, forming a double bond. The fatty acyl CoA forms trans delta 2 enoyl CoA, and the enzyme catalyzing the process is acyl CoA dehydrogenase. In this oxidation step, the molecule being oxidized is the fatty acid. The hydrogens removed from the fatty acyl CoA are taken up by FAD to form FADH2, and this reduced FADH2 can be used for ATP production in the electron transport chain. Here we have a diagram of the molecules undergoing this reaction, and you can see further the removal of the hydrogens and the formation of the double bond. You can see here that the hydrogens that are attached to the carbon 2 and the carbon 3 molecule are removed and joined with FAD to form FADH2, and then we have the formation of the double bond. The second step of beta oxidation is a hydration reaction. This involves the integration of a water molecule. In this hydration reaction, we break the double bond, forming an alcohol at the 3rd carbon. The product formed is L3-hydroxyacyl-CoA. The enzyme catalyzing the reaction is enoyl-CoA hydratase. In this diagram, we can see further the breaking of the double bond and the formation of the alcohol at the 3rd carbon. Step 3 is another oxidation reaction where we see the removal of hydrogens from the fatty acyl intermediate L3-hydroxyacyl-CoA. In this step, the alcohol at the 3rd carbon is oxidized, removing the hydrogen and forming a double bond of a ketone. In this steps, the hydrogens that are removed are picked up by NAD to form NADH. The product is 3-ketoacyl-CoA, and the enzyme catalyzing the reaction is L-hydroxyacyl-CoA dehydrogenase. In this reaction, the NADH that is formed can be used to enter the electron transport chain for the formation of ATP. This diagram further demonstrates the removal of the hydrogen at the alcohol formed at the 3rd carbon and the formation of a double bond forming a ketone. In the last step, we see the cleavage of acetyl-CoA. This step also involves the integration of coenzyme A to form a new thioester bond at the 3rd carbon to make a new fatty acyl-CoA shortened by 2 carbons. This reaction is catalyzed by thiolase. Here in this diagram, you can further see the point at which the fatty acid intermediate, the 3-ketoacyl-CoA, has the cleavage between the 2nd and the 3rd carbon and this liberates the acetyl-CoA, and you can see this acetyl-CoA product here. And then we have the integration of a new coenzyme A, which joins to the third carbon, forming a new fatty acyl-CoA molecule shortened by 2 carbon atoms. You can see in this slide the diagram of the 4 steps of beta oxidation. Including each of the intermediates and the enzymes. The diagram also highlights the second and third carbons active in the reactions of each step. So you see here carbon 2 and carbon 3, carbon 2 and carbon 3, etc. You can also see the NAD and the FADH2 formed in the 2 oxidation steps. So here we have the first oxidation step and the formation of FADH2. And then in step 3, we have the second oxidation step and the formation of NADH. And you see how they outline that the FADH2 and the NADH can then go on through the electron transport chain to form ATP. It will be important to track the NADH and the FADH2 formed when calculating the ATP yield for the oxidation of a fatty acid. Beta oxidation is a continuing process, with cycles continuing to cleave acetyl-CoA. The last cycle begins with a 4-carbon chain producing 2 acetyl-CoA molecules. You can see here in this diagram the beta oxidation being a continuing process, continuing to reduce the fatty acid chain by 2 carbons until you get to the 4-carbon molecule undergoing the last beta oxidation cycle, with the last products being an acetyl-CoA and acetyl-CoA, which can each undergo further oxidation through the Krebs cycle. Odd-numbered fatty acid chains are unique in that the last beta oxidation cycle begins with a 5-carbon fatty acid chain. From this 5-carbon fatty acid chain, there is a cleavage of an acetyl-CoA, leaving then a 3-carbon molecule, the propionyl-CoA. Propionyl-CoA is a unique fatty acid derivative in that it is glucogenic, meaning that it can be converted to glucose through the process of gluconeogenesis. This again is in contrast to acetyl-CoA, which is not glucogenic. The propionyl-CoA can also be oxidized in the Krebs cycle by being converted to succinyl-CoA. And this process of the conversion of propionyl-CoA to succinyl-CoA utilizes 1 ATP. You can see in this diagram the conversion of propionyl-CoA to methylmalonyl-CoA to then succinyl-CoA, which is the intermediate of the Krebs cycle. And you can also see the investment of the ATP molecule. You can see here in this diagram where the acetyl-CoA, which is cleaved from a beta oxidation cycle, enters the Krebs cycle, and then where propionyl-CoA enters as succinyl-CoA. This slide reviews the product yields of one beta oxidation cycle. And you can see with the 4 steps of beta oxidation, we have the products of an FADH2, an NADH, and acetyl-CoA, and with further oxidation through the electron transport chain, we know that 1 FADH2 produces 1.5 ATP. Also through the electron transport chain, an NADH produces 2.5 ATP, and 1 acetyl-CoA, going through one turn of the Krebs cycle with the production of 3 NADH molecules and 1 FADH2, produces 10 ATP. So in total, one beta oxidation cycle yields 14 ATP. Here in this slide, we see the formula used for calculating the ATP yield from the oxidation of a fatty acid chain. Here we see the formula. This formula is specific to the oxidation of an even-numbered saturated fatty acid chain. You can see here for a fatty acid of carbon length 2N, the formula is N minus 1 times 14 plus 10 minus 2. We have the 14 because we saw previously that the ATP produced from one beta oxidation cycle is 14 ATP. We have 10 because in the last beta oxidation cycle we produce an additional acetyl-CoA, and with one turn of the Krebs cycle that acetyl-CoA yields 10 ATP, and we see that 2 ATPs are lost during the first preliminary step of beta oxidation, so we account for that ATP investment. Here's an example of doing a calculation with a fatty acid palmitate, a 16-carbon, therefore even-numbered saturated fatty acid chain. So with a 16-carbon molecule, looking at 2N, we have N equals 8, and plugging in that information, in the parentheses we have 8 minus 1 times 14 plus 10 minus 2. So going through that calculation of 7 times 14 plus 10 minus 2, we get a total of 106. You can try doing a calculation on your own by calculating the ATP yield for an even-numbered saturated fatty acid chain consisting of 10 carbons. This last slide reviews the regulation of beta oxidation. You can see that there are several metabolic signals involved in increasing or decreasing the activity of beta oxidation. We will focus on the third and the fourth lines here. We can see that each of the beta oxidation enzymes are inhibited by the intermediate it produces. Lastly, we see that an increase in NADH or acetyl-CoA reduces the activity of beta oxidation.